presented by Caltech.
So we were talking about damping and driving our oscillator. And so we have this, the general equation up there for a damped-driven harmonic oscillator with a damping coefficient gamma for a velocity, and damping force is proportional to velocity. Then we went ahead and solved. So to solve the inhomogeneous problem, the general inhomogeneous problem, the steps are first solve the homogeneous problem, and then find a particular, get a general solution to that, and then add that to a particular solution to the inhomogeneous problem. And so we carried out the first part of that. We found a general solution to the homogeneous problem. And the next step in principle would be to find a particular solution to the driven problem. But I want to look at this solution to the homogeneous problem first. This corresponds to transient motion where there's no driving force. You just start it with some initial condition that's out of equilibrium, and you watch what happens. So I want to look at these solutions a little bit. So I want to look at the transient response of the oscillator. So there are three other cases that I'd like to isolate. When omega 1 squared is greater than 0, we're up here, and omega 1 squared, if you can see it, is something positive. So we have oscillatory solutions in here. We have sines and cosines coming from these exponentials. So then we have an oscillatory solution. With a frequency given by omega 1, which is less than omega naught. And so our oscillatory solutions have frequencies that are less than the natural frequency of an oscillator. So the damping drags the frequency down. So this is referred to in the book as lightly damped. So that's one of the conditions, one of the possible cases. You can also have omega 1 squared less than 0. In this case, I can rewrite my solution in the form x of t is equal to e to the minus gamma t over 2. And then omega 1 squared is less than 0, so omega 1 is going to be imaginary. So I'm going to replace that with a e to the minus w1t plus b e to the w1t, where I've defined w, or w1, to be square root of gamma over 2 squared minus omega naught squared, just a real number that's bigger than 0. Okay. We see that omega 1, well, it was bigger than 0. It's also, from this condition, it's also less than gamma over 2. So in fact, what we have is we have certainly a decaying solution here. So we have a sum of two exponentials. We have a decaying exponential from the product of these two. We just add w1 gamma over 2 with the minus sign times t. Here we also have a falling exponential because w1 is less than gamma over 2. So it doesn't. So this increasing exponential doesn't overpower this exponential. So they're both decaying solutions. So this is just a sum of two exponentials. It's non-oscillatory. No oscillations going on in this one. When, since you can't see that word, when we have W1 or omega 1 squared equal to 0, then we have this other solution, e to the minus gamma t over 2 times a plus bt. So this is somewhere sort of in between. The oscillatory solution is gone, except for possibly some initial rise with time. This is known as critical damping. This is an interesting case. So I'd like to try to see if I can illustrate this with a picture. Your mission. So, no signal. This yesterday I just. It depends. The problem is it depends on the sequence in which you plug things. I can't even get. There it goes.
Professor, there's a button on there, yeah, which
Just change that to something else. So that should do it. Okay, so I'm showing all three cases here. So this is just a function of x as a function of time against time. Omega naught here is pi, so the period of these oscillatory parts is about 2 seconds. So if we look at the oscillatory solution first, well, I've done it with some initial condition that isn't quite starting at x at 1, so it's a little bit less than x equals 1 here. So it's got this face on there. So it's just oscillating back and forth with a period of order 2 seconds between these two envelopes given by the green. These green envelopes are just this e to the minus gamma t over 2 factor. The omega 1 squared less than 1 case, less than 0 case, is this orange curve here. See, that's this one over here, where it's e to the minus gamma t over 2 times these two exponential factors, where omega is a real number that I've just arbitrarily picked to be 0.4, just for example. And so you see, it's just an exponential fall off. It's actually the sum of these of two exponentials. And then finally, the critical damp solution, which I've taken A and B to be both 1, so it's 1 plus t times the e to the minus gamma t over 2, actually has some initial rise in the beginning because of this t, and then it falls off quite rapidly as an exponential. Well, exponential times 1 plus t. Any questions about the picture before we go into the
For the omega like squared greater than 0 solution, is that just an underdamped solution? Like the
Yeah,
equation?
I thought it would call it lightly damped, but yeah, it's underdamped.
Okay.
Yeah. I don't remember what language different people use. Okay. So those are the different cases that the transient solution can have, the transient behavior of our harmonic oscillator. There's some additional interesting things to learn here. In particular, if I look at the energy of the transient solution, so we have the usual, the energy is equal to the potential energy plus the kinetic energy. I'm still using the mass on a spring as an example. I could be talking about SCR circuit too. The math is just parallel, even if the words are different. So this goes like 1/2 kx squared for potential energy stored in the spring, and 1/2 mx dot squared for the kinetic energy in the mass. It's no longer conserved. Because we have energy loss in the damping. So there's heat being generated that is just being dissipated. X and x dot are both proportional to e to the minus gamma t over 2. So there's some something going on, and so it's going to make them both dot out. So we immediately know that E, the energy of time, as a function of time, is going to be e to the minus, I have to square this, it's squared in both places, gamma t times some function of time. But it's at least going to have this damping factor out front. So that gamma has something to do with the rate of energy loss of our system. So we could consider all three cases in great detail, but let's not do that. Let's just take one of them, for example, here, which is usually the one people do. It's kind of interesting. Let's consider the lightly damped case. And look a little bit more detail at what happens there. So let's write x of t. So in general, x of t is some function, oscillatory function there. So I'm going to write it in terms of the cosine instead of in terms of a's and b's. So I'm going to write it in terms of some amplitude times the cosine of omega 1t plus phi, and then it has the damping factor, e to the minus gamma t over 2. Omega 1, remember, is just square root omega dot squared minus gamma squared over 4. So we take the derivative, x dot of t is equal to, okay, well we take the derivative, it's going to be a c e to the minus e to the t over 2 times everything. And then there'll be, from taking the derivative of this, there'll be a minus omega 1 sine omega 1 t plus phi. And then taking the derivative of this one, we have a minus gamma over 2 times cosine omega 1 t plus phi. Okay, so now I take E, I plug this in, I plug this in, and I calculate. So I have to take the square of this, square of that, add them with some coefficients. I'll keep in mind this relation that omega 1 squared is omega 0 squared minus gamma over 2 squared, and that k over m is just omega 0 squared. Okay, keep those things in mind. So I'm not going to do the algebra here. I'm not going to take the time to do the algebra. It's straightforward and a little tedious. I encourage you to do the algebra and work it out. You get E of t is equal to 1/2 mc squared, which is my e to the minus gamma t factor, times k over m, which remember is omega 0 squared, plus gamma over 2 squared cosine of 2 omega 1 t plus phi plus gamma omega 1 over 2 sine of 2 omega 1. Yeah, okay. Omega 1 t plus phi. That's it. And then I have to close my bracket somewhere. So, one thing to notice is by assumption, this is greater than gamma over 2 squared. So this term dominates this term, and if you think about it, it dominates that term too. Okay. It's bigger than those terms. Notice that it's twice the frequency. Twice omega 1. We got sines times cosines and sines and cosines squared, and then combined in such a way to just give us precisely these terms when we did the trig relations. So we actually have that this energy as a function of time is varying sinusoidally. Since this term is bigger than these terms, it's almost positive, which you hope it will be. I hope you hope that. So we're not violating any laws of physics here. So this is greater than 0 for all time. So, okay, so this is it. This is how the energy behaves as a function of time. One could look at it in more detail. An interesting special case, yeah.
Sorry, when you said the energy is varying sinusoidally, is that the total energy or it's just moving between the two parts?
This is U plus K
Right.
that I've calculated here. So that's the total energy.
Okay, but that's not going up and down.
So it's not the energy being lost in friction.
Okay.
If I were counting that, then it would be a constant.
But it's not going to go up, is it? It's not gaining any energy at any point?
Oh, yeah, no, it's got this exponential envelope on it.
Okay.
So it's got oscillations that are going up and down,
Okay.
times an exponential envelope. I mean, locally it's going up and down.
Okay.
Okay, so let's see. So let's take an interesting special case. Let's consider very light damping. suppose that our natural frequency is much larger than our damping constant. So the damping is very small. In that case, these terms are negligible compared to this term. And so I'll just drop them. Okay? E of t is approximately 1/2 k c squared times e to the minus gamma t. Or I can write that as the energy at time t equals 0 times e to the minus gamma t. Where e of 0 is just 1/2 kc squared. That's the energy. So if we had removed the damping, this would just be the energy of the undamped. Oscillator. So this is an example of an exponential decay law. Which we encounter quite a bit. If I let tau be 1 over this coefficient gamma in here, then we just have E equals E naught e to the minus t over tau. Tau is what we might call the energy lifetime. Of the oscillator. It's telling us how long it takes to decay a certain amount. We have to decay a fraction of 1 over e from the initial energy. Tau has the property that if I ask for, if I look at this as some distribution and I want the average of the distribution, I will take the average time. I want to take the average time in this exponential decay law. I would take t times this 1 over tau is chosen such that this integral without the t there is equal to 1. So that I can really consider this exponential to be describing a probability distribution, probability of any given value of t, according to the energy. This is just equal to, so this is just by definition the average value, or the mean value of the time, according to this energy weighted distribution. So in general, if you have an exponential decay law that you think of maybe a little more in terms of probability, such as a radioactive decay law, it's an exponential. In that case, tau would be the mean lifetime of the radioactive decay, of whatever it is that's decaying. So we can talk about a half-life too. So here tau is the time that it takes for the energy to decrease by a factor of 1 over e from its initial value. The half-life of the oscillator, which we can call E, that's where the energy decreases by one factor of 1/2 from its initial value. So if I calculate that, e to the minus t 1/2 over tau is equal to 1/2. So when t is t1/2, this factor should be 1/2. Yeah.
How does like defining tau in terms of itself work? Like why is that okay?
Oh. So, yeah, I agree that's confusing. Yeah. Okay. I'm calculating the average value of the time. By definition, it's this. If I do this integral, I get tau. Okay. So I can too big a shortcut there. Okay, so we get so I'm going to calculate t1/2. So I just take the log of both sides, and so I get t1/2 is just equal to tau times the natural log of 2, which is around 6 point. So it's around 0.7. So the half-life for an exponential decay is about 70% of the lifetime. Okay. So if you ever want to need to convert between these. Let's let t0 be the natural period of the oscillator. That is the undamped period. So T naught is 1 over the natural frequency in hertz, say, is equal to 2 pi over the angular frequency in radians. So if tau is much, much bigger than T naught, that's the same statement as omega naught much bigger than gamma. So this is very light damping again. Just plug in the definitions of these in terms of gamma and omega naught. Let's see. What does this mean? If tau is much bigger than T naught, omega naught is much bigger than gamma. Omega naught is much bigger than gamma. So omega 1 is close to omega naught. So my oscillatory solution is roughly going to be at the natural frequency at omega naught. And so if tau is much bigger than the period, that is, if the decay time, the characteristic time for decay of the oscillator, is much greater than the period of the oscillation, then we're going to have many oscillations in one decay time. We have many oscillations in one lifetime of my oscillator. Lifetime tau. So it's going to be oscillating like this and not decreasing very fast. It's going to almost be constant, almost our undamped oscillator, just go slowly down. So there's a useful quantity. We can consider the number of oscillations in one lifetime and calculate that. Well, roughly speaking, that's just tau over T naught. Because we're just going lifetime is tau, and the period of the lifetime, the period of an oscillation is T naught, so the ratio is the number of oscillations in that time. And so what is this? This is 1 over gamma times omega naught over 2 pi, or 1 over 2 pi omega naught over gamma, trivial rearrangement. And this is a useful quantity here. This is a characteristic of our oscillator. It's just in terms of how much damping there is and the natural frequency. So this gives us some notion of how good our oscillator is in terms of whether it's highly damped or not damped. So we define what we call a quality factor, called Q, capital Q, standard nomenclature, which is just defined as omega naught all again. So for high Q values, you're going to get very slow damping in terms of how many oscillations you get. There are many oscillations before you lose as much energy. And so, chapter 2, if you read chapter 2, it has a table of Q values of various common oscillators. They list some values that go up to 10 to the 6. But they could have listed another one. Superconducting RF cavities, such as people use in modern accelerators. They can have Q values that are extremely large. Okay, Q values up to a few times 10 to the 10th even. Much larger than the examples in the book. So let's say that these superconducting RF cavities are so good that you can get 10 to the 10th oscillations. So you just turn off the grinding voltage and see what happens. It'll just keep ringing and ringing and ringing and ringing 10 to the 10th times before it's gone one lifetime. Like the oscillator. Yeah.
Is that definition of the quality factor for all kinds of oscillations or only very like damping?
So you have a homework problem on that. Okay? So yeah, so you just generalize it to all cases.
Okay.
Okay, so let's just go a little bit further with this. Let's consider, so this Q is a nice characteristic to know about your oscillator. Let's consider the energy lost in just one oscillation. Just want to show that Q's quality factor shows up in different contexts. So let's see, how do we do that? The energy lost in one oscillation, so delta E, that's going to be energy lost in one oscillation. So it's the energy that I started with at whatever time I'm comparing things, minus the energy after one oscillation. So after one oscillation, I have e to the minus gamma. Why did that put it? Gamma times t. It's confusing me. So one oscillation is a time t naught later. So I just want to take that difference in energy. It's energy lost in one oscillation. So I can write that as e naught, e to the minus gamma t as a common factor times 1 minus e to the minus gamma t naught. So it's useful to think in terms of the fractional energy loss rather than the absolute energy loss, because if I look at the fractional energy loss, it's going to be independent of time. So it's going to be some characteristic energy loss, and I've got to move over somewhere here. So the fractional energy loss, well, both of these are functions of time, but in the ratio, the time cancels out. 1 minus e to the minus gamma t naught. Okay, so I can rewrite that as 1 minus e to the minus 2 pi gamma over omega naught. Plugging in what t naught is. But this is 1 minus e to the minus 2 pi. There's our quality factor there, so it's 2 pi over q. So now if we have very light damping, we have a large Q value. So let me just look at this for large Q. So for large Q, this is going to be a small number. I'll do my Taylor series once again. I'll do a Taylor series of e to the minus x about x equals 0. And we get just delta E over E of t is equal to, well, there's that 1, and then 1 minus the e to the minus 2 pi over gamma, which I'll expand on the power series. First term is 1, then minus 2 pi over q, and then thus order of 1 over q squared, which I'll neglect because q is big. So to first order, the first non-zero order here, the ones cancel nicely, I get 2 pi over q. So 2 pi over q tells me the fractional energy loss in one cycle of the oscillation. So that's another physical way to think about what q is. We also have the frequency shift. Omega 1 squared is equal to omega naught squared minus gamma over 2 squared. I can write this as a common factor of omega naught squared. That is 1 minus gamma over 2 omega naught squared. Just rewrite that a little bit. But now you see q coming in again. Okay. Or I could just write, using the square root of this, omega 1 is omega naught times the square root of 1 minus 1 over 4 q squared. So again, so q tells us what the shift in the frequency is of our damped oscillator, and if q is very big, the shift is very small. So I just want to point out, we have the corresponding discussion to all of this. This all just follows through for the LCR circuit. So now that we've done the spring, you can do the LCR circuit. So that's the, the LCR circuit with the capacitor. And I'll put the resistor up here, resistor, and the inductor. And the idea is we have some charge as a function of time on the capacitor, and that generates some R of t, which is just q dot of t, going around the circuit. So you analyze this by saying the sum of the voltages around the loop is equal to 0. You have to come back to the same potential you started with. If you go around the whole circuit. And so that gives you the equation Q over C plus L Q double dot, which is di by dt, plus V equals I times R, just Ohm's law, is equal to 0. So that's the sum of the voltages going around the loop equal to 0. And my vector goes somewhere else. Oh, that's interesting. I haven't had to erase yet. Oh, it's too bad. Okay, so what do we do? The natural frequency we already know is 1 over the square root of LC. Gamma, just compare this equation with the spring equation and read off what gamma is. Gamma is R over L. Now that I've erased the spring equation. Okay. The X in the spring is just Q. Okay. And so now, then it's completely equivalent. Our solution for X in the spring problem now becomes the solution for Q in the LCR circuit. All right. That's transient response. There's lots more interesting things to say about transient response, but I would like to move on now to solving that damped driven harmonic oscillator equation. I've got the general solution to the homogeneous problem, that is the solution to the transient response. I need to find a particular solution now to the inhomogeneous problem. That is the driven damped harmonic oscillator. So let's write our equation in the following form. So instead of that cosine omega t driving force, I'm going to just generalize to an arbitrary phase and amplitude driving force, and I'm going to use e to the I omega t kind of notation. So I'm going to write, okay, I'm going to take the real part of this equation. Okay. And that'll give me the equation that I had. X double dot plus gamma x dot plus omega naught squared times x is equal to my driving term. Omega is the driving frequency. Before I said that A naught was F over M, where F is the magnitude of the driving force. I'm going to allow it to have a phase on it that might not be zero. And of course, since I'm writing F over M and M there, I'm thinking in terms of the spring problem, but of course I could do the same thing for the LCR circuit, just by changing my symbols a little. All right, so what do I do?
Professor,
Yeah.
can you clarify the real part of that whole equation? What does that express?
So, well, in the end, I want x to be something empty. And so this is just a device to allow me to write general sines and cosines. So I want to be able to have this reduced to cosine omega t plus phi. So that side, what I really mean is cosine omega t plus phi, which is precisely the real part of what I've written up there.
Thank you.
And so now I have, the possibility of general amplitude and the general phase here. Okay. So I want to find a particular solution to this. I know the solution to the homogeneous part, which I can add to any particular solution and still have a solution. Okay. So, particular solution. I got a bunch of derivatives of x with some coefficients. Is all equal to something times e to the I omega t. So there are various techniques one might try to apply to get this, but one of them is just to guess the answer and see if you get it right. You might guess wrong, in which case you'll find out you got it wrong and you have to try again. But the obvious thing to sort of guess here is because you know there's a sinusoid with an omega t dependence there, is to try a solution that has a sinusoid with omega e to the I omega t kind of dependence and see if it works. Try x of t is some constant times e to the I omega t. C may be complex. We'll find that out as we go along, whether it's complex. It has, yeah, okay, we'll find it out. So we could try the solution. What do we do if we have a solution? We plug it in and see if it works. If it works, we're done. We only want to find one solution. We're not trying to find the general solution because we know if we add the general solution to the homogeneous equation, which we already know, if we add that, then we will have the general solution. So we just need one solution. Minus c omega squared. So I'll take, fortunately it's easy. Double dot of this is going to be just a minus omega squared times x. So I'm going to leave out the x's here because every term is going to be, well, the x's. I'm going to leave out the e to the I omega t part because every term is going to have an e to the I omega t in it. Just divide it out. I omega c gamma, there, plus omega naught squared times my constant c, and that's all equal to a naught because I divided through by e to the I omega t. That wasn't hard. The only unknown here is c. Everything else is given to us. So this works as long as c is just equal to a naught divided by all this stuff that's multiplying down here, which is omega naught squared minus omega squared plus I omega gamma. So we've done it. We are done. Here's my, there. we've really accomplished that. We found the general solution to our damp-driven harmonic oscillator. And that covers a number of physical situations, so it's a nice thing to know. So x of t is equal to, I won't write it down again, the general homogeneous solution with its different cases, plus this solution, particular solution to the inhomogeneous problem that I'm focusing on now. Omega naught squared minus omega squared plus I omega gamma times e to the I omega t. So if there's an oscillatory solution in this yeah.
Do we want the real part of that, or are we leaving I?
So implicitly, we're going to take the real part in the end.
So calculate that, and that's the bigger part.
So in general, I just take, you know, is equal to the real part of this.
Okay, so
Yeah. So we often don't write that explicitly. So we've done it. We can go home. Well, okay, but you know, this had some rich behavior in it. This has some rich behavior in it too. The oscillatory behavior in this had some frequency that was characteristic of the oscillator. The oscillatory frequency here is whatever the driving frequency is, so that's something useful to remember. And then we've got this factor out front. And there's some interesting things going on there. And so next time we'll look at that some of that interesting behavior. We'll look at this factor and try to understand it a little better. And then we'll go on to finals.